start the recording. All right, hello. Does anybody have any questions before we start? Anything wanted to ask about last time, or life in general? All right, everybody's doing okay? Graded on a curve for the general world situation. Whew. So I wanted to switch gear a little bit. Basically, I had hoped earlier to talk about Poisson geometry, and I kind of realized, there's a real danger in this course that you just kind of say like, hey, here's this object, here's this object, here's this object, like here's a symplectic form, here's a contact form, here's a Poisson bracket. And you can just kind of go through minor variations until your head starts spinning. And that these things are only interesting if you have some interesting examples to think about. So I wanted to talk about moment maps before we talked about Poisson geometry, because that's going to give us one of our most interesting examples. Okay, so we talked about Hamiltonian mechanics and the structure of the Poisson bracket and how it describes things. So one kind of nice way to think about Hamilton's equations is they tell you how observables change over time. And the formula for how they change is that the time derivative of an observable at any given point in your phase space is the Poisson bracket of that observable with the Hamiltonian. Where here, Poisson bracket is defined in terms of the symplectic form, right? We again use this kind of strange definition where xf and xh depend on the symplectic form. They're found by solving a linear equation involving the symplectic form, and then you put them back into the symplectic form, and you get a function. But we could have kind of done this the other way around and said, wait a second, I'm not using a symplectic form in Hamilton's equations, I'm using a Poisson bracket. So maybe really the Poisson bracket should be the basic object here, not the symplectic form. Well, then you kind of think about what that would mean, and you come to this abstract notion of a Poisson algebra, which I think was discussed in Kenneth Silva a few chapters ago. So that's a commutative algebra, a ring, which is an R vector space, and such that the ring operations are linear maps. And then an operation on this algebra, which is a bilinear map from the algebra to itself. So something that takes in two elements of the algebra and spits out a third one, which has to satisfy the properties that this operation on its own is a Lie bracket. So it's anti-symmetric, satisfies the Jacobi identity. And that there's a compatibility between the Lie bracket structure and the commutative multiplication, which is given by the Leibniz rule. So if I take A times B and then take the Poisson bracket of that with a third thing, this is saying that Poisson bracket with that third thing acts like Lie derivative with respect to a vector field. And in fact must be Lie derivative with respect to some vector field if you're on a manifold. So if you like thinking about things in terms of abstract algebra, this says that the function A maps to AC is a derivation. And if you've never heard of derivations before, well, there's the definition. They're a function that satisfies the Leibniz rule. All right, so that's a sort of abstract algebraic notion. And then a Poisson manifold is just a smooth manifold such that the smooth functions on it have a Poisson algebra structure. That's one definition of a Poisson manifold. That's kind of the most algebraic one. Now, if you go look at a book about Poisson geometry, I think actually it's more likely that it will tell you that a Poisson manifold is a manifold that's equipped with a bivector field. I said bivector, but I really should have said bivector field. So that's a section of the vector bundle, second wedge power of Tm. So this is something which to every point in the manifold, let me just kind of emphasize this, for each point in the manifold, I have that pi sub p is in the second wedge power of the tangent space at P. So, right, a vector field is when you choose just an element of the vector of the tangent space. Now I'm choosing, this is sometimes called a bivector field, of element of the second wedge power, which includes the second tensor square. So this is one example of a higher order tensor. I think it's right to call this a 2-0 tensor, though sometimes I get the order of those wrong, so I won't absolutely swear that's right. All right, now given this bivector, well, an element of the second wedge power of the tangent space can eat an element of the second wedge power of the cotangent space and spit out a number. So like one way of sort of trying to define what an element of the second wedge, section of the second wedge power of the tangent space is it's something that eats two forms and spits out numbers in a tensorial way. So I can have this guy eat the two form df wedge dg, and that spits out a function which I define to be the Poisson bracket of f and g. And again, there are sort of some choices you can make about the right way to write this definition. One way is just to say, I impose the condition that this is a Poisson algebra structure. So that's an additional condition on pi. It can't just be any old bivector field. It has to induce a Poisson algebra structure. Now this is actually equivalent to the definition I had before. And the heart of that is just the observation that if I have any operation that goes from C infinity functions on a manifold to C infinity functions on a manifold that satisfies the Leibniz rule with respect to multiplication by any function, then it must be Lie derivative with respect to a vector field. So if you have a Poisson algebra structure, then for every function, you can define a corresponding Hamiltonian vector field as the unique vector field that satisfies that Poisson bracket with f is Lie derivative with respect to f. With respect to xf. All right. So this is just using sort of, some people will define vector fields as derivations of the algebra of C infinity functions to itself. That's one way of defining what a vector field is. And so you just say, oh, well, I think about that as a vector field in the normal way. And that's my Hamiltonian vector field. And I'll just mention here, right, this Lie derivative only depends on dg. So this formula also tells you that the Poisson bracket of f with g only depends on dg, and by symmetry, it only depends on df as well. So that tells you that sending df to xf is actually defined by a map of bundles, right? So this word tensorial, I heard this used many times before I understood what it actually means, but it just means induced by a map of vector bundles, right? It means that it comes from a map from the vector bundle T star F T star of m to T of m. It doesn't depend on choosing any derivatives or anything like that. It's purely defined in terms of what's the value of the one form df at a given point, apply a linear map, and that tells me xf. All right, well, by some basic linear algebra, a linear map from the dual of a space to the space is the same as an element of the space tensor itself. So we can turn this into a section of T of m, and that section actually lies in the second wedge power because Poisson bracket is antisymmetric. All right, are there any questions about this argument? This is just sort of explaining why any Poisson bracket actually has to come from a bivector. That's the only takeaway here.
I have a question. How do you get the symplectic form from this structure? Is it just the dual of that section?
I was going to say this later.
Sorry.
The way you get the symplectic form is you if this map from T star of m from the cotangent bundle to the tangent bundle is an isomorphism, then you can take its inverse and you can think of that as a section of the second wedge power of the cotangent bundle. So this defines a symplectic form if and only if this map is actually an isomorphism of bundles, which it might not be.
Oh, I see. Gotcha. Thank you.
Mm-hmm. Yeah, I was going to get to that later.
Okay.
Because I wanted to discuss another like little kind of nook and cranny of this definition, which is, so if you have a bivector, then antisymmetry just comes from the fact that you're taking something in the wedge power. The Leibniz rule just comes from the fact that it's a bivector field. So those are automatic. And then there's the Jacobi identity, which I just said, well, Poisson bracket has to satisfy the Jacobi identity. So this is some extra condition on pi, which you should think of as kind of being analogous to asking a symplectic form to be closed. When you prove that the Poisson bracket that comes from a symplectic form is closed, actually the proof is that the Jacobi identity for three functions going into the Poisson bracket is equivalent to putting those functions into D of omega. Or sorry, putting the Hamiltonian vector fields into D of omega. But there's actually a sort of better way of expressing this, and I don't want to get kind of deep into this, but on multi-vector fields, wedge powers of vector fields, there's a way of extending Lie bracket called Schouten bracket. It's one of these weird Dutch names, but it's Schouten. Such that pi defines a Poisson structure if and only if the Lie bracket of pi with itself, or sorry, the Schouten bracket of pi with itself is 0. And this is again like writing out, basically, if you write out this sort of definition of Schouten bracket, you see that pairing, whoops, I should just go a little further over, pairing the Schouten bracket with df wedge dg wedge dh is exactly sort of the quantity that the Jacobi identity asks you to prove is 0, which, if you want to be fancy, you call the Jacobiator. So it's the taking this Lie bracket of all cyclic permutations of these guys. All right, and you have to know what the definition of Schouten bracket is to check this, but it's not extremely deep and difficult. So there is a kind of more invariant way of saying what a Poisson structure should be, that it's a bivector field whose Schouten bracket with itself is 0. And then I'm just writing out this observation I made in response to Matthew's question, that if the induced map from T star to Tm is an isomorphism, I can take its inverse, think of that as a map from the tangent bundle to the cotangent bundle. That is contraction with some 2 form. And that 2 form is a symplectic form, if and only it applies a Poisson bracket. And the original Poisson bracket is the Poisson bracket we defined in terms of symplectic forms before. So this is sort of a strict generalization of the notion of a symplectic form. And there are lots of Poisson brackets that are degenerate, that aren't non-degenerate. So just as a dumb example, taking pi equals 0, well, certainly the Schouten bracket of that with itself is going to be 0. So that's a perfectly good Poisson structure. It's kind of a dumb Poisson structure, right? It just says that the Poisson bracket of f with g is always 0, but it satisfies the definition. All right, so why do we think about Poisson manifolds? One answer is, I mean, I really think that if you sort of go through Hamiltonian mechanics, like the Poisson bracket is a more basic operation than symplectic form. So one way I think you can see this is that the relationship between classical mechanics and quantum mechanics, I would usually write in terms of the Poisson bracket, right? So if you have observables f and g in classical mechanics, those quantized operators in quantum mechanics, usually people represent as f hat and g hat. And what you get is, well, now these operators don't commute with each other. This is like, you know, why people say that non-commutative stuff is quantum. And so I can take their commutator, and the sort of first order bit of this commutator in, you know, in terms of Planck length is the Poisson bracket. So it's sort of the first order bit of this quantization. And so you can sort of say that Poisson bracket is the leading order of commutator operators in quantum mechanics. And people will use this term semi-classical to refer to sort of the geometry of a manifold with a fixed Poisson structure, that it's sort of remembering some of this quantum mechanics via the Poisson structure, but not remembering everything. Are there any questions? Okay. So as I say, I didn't sort of want this to be a just like, oh, hey, here's another definition, right? I honestly, like, I skipped the contact section of Canis de Silva in part because when I sort of started thinking about what the lecture was going to be, it was like, oh, basically like, okay, here's the definition. Here's another definition. Here's another definition. And I don't think that's very useful. So I think it's better to think, what's it to go through an interesting example of a Poisson structure that isn't symplectic. And for me, the most interesting example is what's called the Kostin-Kirillov-Suryow. Should probably actually write that out. Suryow. You'll also sometimes just see Kostin-Kirillov Poisson structure on the dual of a Lie algebra. So you'll note here, right? This is kind of taking us back to thinking about moment maps. The dual of a Lie algebra is showing. And what is this? So an element of the Lie algebra I can think of as a linear function on the dual, right? This is how dualizing vector spaces works. And just to avoid any confusion, I'm going to use a different name for this. I'm going to call it f sub x, if x is the element of the Lie algebra. So f sub x, that's a linear function on G dual. And the Kosten-Kirillov-Surya-Poisson structure is the unique one where the Poisson bracket of f sub x and f sub y for two elements of the Lie algebra x and y is equal to f sub the bracket. So the Lie bracket, the Poisson bracket on linear functions is the same as the Lie bracket on the original Lie algebra. And this is another one of these things where there are minus signs floating around, having this terrible feeling of like, oh, Silva defined the opposite of this and put in a minus sign. I don't think I carefully checked, but so you'll sometimes see this with a minus sign in it.
I'm sorry, how is this not, it seems like you haven't really done anything, like you've just kind of taken the dual and then transported the Lie bracket.
Well, yes,
but to the G double dual.
This Poisson bracket defines an operation on all functions on G dual.
All functions, not just
linear ones. Right. So I'm saying on the linear ones, the Poisson bracket is the original bracket.
Strange.
But
okay.
And if you just read the rest of what's on the slide, you'll see why that's the only thing we need to check to define the Poisson bracket, right? If you sort of want to be convinced that such a Poisson bracket exists, I think the easy way to do this is to just pick a basis of the Lie algebra. You get structure coefficients for the bracket, and then you can write out exactly what this Kosten-Kirillov-Surya, the actual Poisson tensor in terms of these structures, right? It's you take ddxi and ddxj, wedge them together, multiply them by the linear function f xk, and then by the structure coefficient xkij. And I at least think I've set this up correctly so that when you take the Poisson bracket of f of xi and f of xj, right, what's happening here? What happens when pi eats dxi wedge dxj, right? So by definition, the Poisson, I should have written, sorry, these should have been, okay. I want to take the Poisson bracket of f sub xi, f sub xj. That means I take d f of xi, d f of xj, and have them be eaten by these guys. So what I get is sum over k do ckij f of xk, and this is by definition f of the Lie bracket f of xi bracket xj. All right, so I can explicitly write out this Poisson tensor, and now I can take any function on G dual and feed it into this. Maybe slightly fancier but coordinate independent way to think about this is what I'm saying here is if I have an element of G tensor G dual wedge square, I can think of the elements of G dual as vector fields on G dual. And I can think of the element of G as a linear function. And then I think of the Lie bracket as an element of this space. So the Lie bracket itself as a bilinear map can be thought of as an element in here. And I'm turning that into a bivector field via this map. So that's kind of a little harder to think about, but it doesn't involve choosing a basis. So it's a bit kind of nicer.
Quick question,
Yeah.
like, and I have an even stupider way to think about it, or I have a stupider way to think about it instead of a smarter way to think about it. Can't we say that the algebra that we're trying to put a Poisson structure on is just a polynomial ring in these fxk?
I think that's a reasonable way to think about it. One thing I will say is, no, I want all smooth functions on G dual.
Okay.
And, you know, yeah, I think there probably is some fancy way of saying like, oh, but that's like some completion of the polynomials. And like, I think you could make it work. I feel slightly better just writing down the damn bivector.
Sure.
But yes, I mean, like, you know, if you gave me sodium pentothal, like that's the explanation I would give you for why this Lie bracket exists. And actually, no, I would say like, oh, actually, you take the universal enveloping algebra and you know, do a limit like this thing I wrote with the quantum mechanics.
Huh.
So this is the semi-classical limit of the universal enveloping algebra of G for people who like that kind of way of thinking about things. All right. Any other questions? Any other proposed constructions of this?
Yeah, I mean, couldn't you, doesn't a derivation in general, isn't it determined by what it does on generators? So the algebra, if the algebra were generated by, I guess that's exactly what he was saying, right?
Yeah.
A polynomial.
I mean, you know, like I think you could make this work, but to me that sounds more complicated than just saying, you know, here is the bivector. It's obviously the only bivector that gives you the right Poisson bracket on linear functions. And so it's obviously the right thing, right?
Yeah.
And
Okay.
say, you know, somehow like if you write out what it means to take the Schouten bracket of this guy with itself, you're exactly going to get sort of the formula that's kind of the consistency for structure coefficients for the Jacobi identity to hold. I'm not going to like write that out, but that's like exactly what you'll find, that this guy is a Poisson structure because the original Lie algebra satisfies the Jacobi identity. Josh.
Yeah. So trying to understand the Schouten bracket, like, do you have kind of a geometric intuition for this thing in general? Like when you look at bivector fields, at least, if you like in the case of a Poisson structure, the vanishing of it ensures that you get this nice symplectic foliation, right? And so kind of the bracket is to some extent like measuring the degree, the non-integrability of this bivector field, right?
Maybe. Like I could believe you that there's some interpretation in those terms, but I honestly can't say. I mean, you know, yeah, that's sort of, yeah, I haven't thought carefully about like exactly what goes wrong if the Schouten bracket of this guy with itself is non-zero. I can certainly believe that like one of the issues, right? So one of the nice things about a Poisson bracket, right, is that you still have this equality that the Lie bracket of two Hamiltonian vector fields is again a Hamiltonian vector field. And that's like one of the things that would go wrong if you didn't have the Jacobi identity. This is like right? This is exactly because of the Jacobi identity H of this guy is equal to right. So this equality is another way of writing the Jacobi identity. I think. Well, anyways. And yeah, I mean, this is sort of at least morally why you get some integrability of. We're going to talk in a minute about like this giving you a foliation, and you're right that that's kind of somehow what would go wrong. But I don't have a good sort of explanation of like in general what it means to take the Schouten bracket of a bivector field with itself. I mean, whatever the failure of the Jacobi identity for the, right? So for any bivector field, you can define a bilinear operation that, you know, by the same formula we use for the Poisson bracket, and it's not going to be a Poisson bracket. And so like the Schouten bracket is like measuring the failure of the non-triviality of the Jacobiator for that guy. But like what that means geometrically, I mean, it's some kind of like curvature, right? It is something about sort of like a failure,
right? Because you have blades of
that capture the bracket of the corresponding vector fields.
Okay.
That's about as good as I can do. Right, yeah, okay, good. By the way, just for those of you who didn't quite capture the significance here, this thing on the right-hand side is exactly the Lie derivative of H with respect to the Lie bracket of these vector fields. And whereas this on the other side is the Lie bracket with respect to this guy. So the Jacobi identity is exactly capturing this equality, which does make it feel a bit like, you know, a sort of curvature type thing, right? It's measuring some failure of something to preserve the Lie bracket. All right. Any other questions? So I really like this example, and this is sort of, at least for now, the only kind of non-trivial example of a Poisson bracket I want to talk about, but it's a really great one. And in particular, it's one where you get a very interesting result out of applying one of the most basic results in Poisson geometry. So as Josh kind of referred to, when you have a Poisson manifold, then there's a unique way of breaking it up into Poisson submanifolds. So I should probably say here, N in M is a Poisson submanifold if the Poisson bivector field restricted to N is tangent to N, i.e. it's in the second wedge power of the tangent space, the tangent bundle to N, which sits inside the second wedge power of the tangent bundle to M restricted to N. Right, so the issue is if you have a submanifold and a Poisson manifold, then when you look at some point on that submanifold, the Poisson bivector might be pushing you off of it. So this is equivalent to the Hamiltonian vector field XF is tangent to n for all f. So a Poisson manifold is one where a Hamiltonian vector field can't push you off of it. And I'll just note this is equivalent to if f vanishes on n, then the Poisson bracket of f with anything else also vanishes on n. So if you like algebraic geometry and you like defining things as the vanishing sets of other stuff, right? This is sort of saying, oh, well, you're the vanishing set of a particular kind of ideal, one that's closed under taking Poisson bracket with anything else. And how are 2 and 3 equivalent here? Well, you know, what 2 is telling you is that when you, if something vanishes, and so I probably should have, maybe I'll actually switch this to G. So this is saying that, you know, if G vanishes on n, then this Poisson bracket of G with f, well, that's the Lie derivative with respect to f of G. Right? And so if G vanishes on n and this Lie and this Hamiltonian vector field just pushes me to some other point on n, well, it's still going to be vanishing there, right? Whereas if at any point a Hamiltonian vector field that pushes me off, then I can choose some G that vanishes on n, but is non-zero in the direction I get pushed off. And so this Poisson bracket won't vanish on it.
I'm sorry, quick question.
Mm-hmm.
How are we talking about Hamiltonian vector fields without a symplectic form? What am I missing?
This definition that I gave before, that you think of Poisson bracket as a derivation, and then you say, oh, a derivation, that's the same thing as Lie bracket with respect to a vector field.
Okay, got it, thanks.
And I mean, actually, like, you could, yet another way you could define a Poisson structure is to say, I have a way of assigning to each function a vector field which satisfies yada, yada, yada properties.
Okay, okay.
So really, you should think of the Poisson structure as the information of which function goes to which Hamiltonian vector field.
I see. Okay.
Right? Like in classical mechanics, that's the basic thing. That when you have an energy function, what's the time evolution? Right? And that's what the Hamiltonian vector field is. So yet another way to say it would be sort of solving these Hamilton's equations. I find the vector field where that makes this equation correct if I know what Poisson bracket is. All right. Okay. Right. So here I was discussing what a Poisson manifold is, but it's a submanifold that actually has an induced Poisson structure. Right. And yet another way to think about this is my Poisson structure. It's some bivector. General submanifold. Well, it's just going to point off in some other direction, and it isn't going to make sense to talk about restricting the Poisson structure to my submanifold and actually being a Poisson structure there. So it's a submanifold there where it makes sense to inherit the Poisson structure. All right. So given any Poisson manifold, there's a unique way of partitioning it up into Poisson submanifolds, which are symplectic. So where this Poisson form actually is non-degenerate. And in fact, as Josh was kind of referring to, you can think of this as kind of the foliation that's generated by looking at all Hamiltonian vector fields. So you can think of these as the equivalence classes of the equivalence relation, where you say that any 2 points are equivalent if there's a Hamiltonian vector field that will flow you from one to the other. And the resulting submanifolds are called symplectic leaves. So a dumb example, but one that's always worth keeping in mind is, what if the Poisson structure is 0? Well, then all Hamiltonian vector fields are 0. You can't go anywhere, and every point is its own equivalence class. So if pi is equal to 0, every point is its own symplectic leaf. And indeed, a single point is a symplectic manifold with the trivial symplectic structure. So the theorem holds in that case, but in a very dumb way, because that's a very dumb Poisson structure. On the other hand, if your Poisson structure already came from a symplectic form, then there's just one symplectic leaf, which is the whole manifold. There's one small lie there, which is that's only right if the manifold is connected. All right, so I should have added in here the condition that M alpha is connected. Because if I have a non-connected manifold, it can perfectly well have a symplectic structure. That's fine. And obviously this equivalence class is never going to get you between two different disconnected things. All right, so maybe that's a good spot to take a short break. And we'll come back and discuss this a little more. So are there any questions people thought of while we were paused? All right, cool. So we've talked about the kind of dumb examples of Poisson manifolds, and this theorem holds, but in a kind of boring way for them. So what about when we put in a kind of intermediate example where the Poisson structure is non-trivial, but it's not completely non-degenerate, which C star always gives us, G star always gives us an example of. Maybe I'll just note, since I didn't say it before, on G star, what happens when I take the bivector pi at 0? Well, that's equal to some sum ckij fk of 0 ddxi wedge ddxj. Oh, well, f of 0 is a linear, f of k is f of xk is a linear function, so it's 0 at 0. So this is 0. So this Costin-Kirillov-Suryaev bracket, it's never symplectic, never gives you a symplectic form on all of G star. It's always a example of a non-symplectic Poisson structure. If your Lie algebra is abelian, then you just get pi equals 0 and it's boring. But as long as your Lie algebra is non-abelian, you're getting an example of a non-trivial Poisson structure that is not symplectic. Okay, so for any non-abelian Lie algebra, this is kind of an intermediate thing between the Poisson bivector being 0 and it giving you a symplectic form. And a cool theorem is that the symplectic leaves of G star for this KKS structure are exactly the connected components of the orbits under the coadjoint representation. These are what are called coadjoint orbits. So I sort of often, a lot of people have heard of the theorem that coadjoint orbits are symplectic, but really they should have heard of the theorem that G star has a Poisson structure whose symplectic leaves are the coadjoint orbits, which I mean, many people have, but some people sort of know is this free-floating fact that coadjoint orbits are symplectic, and where it really comes from is this KKS structure. All right, so how do we prove this? Let me at least give you kind of a loose argument. So given an element of G dual, I need to think about what are all the Hamiltonian vector fields passing through this point. So we need to consider a function f, and we're interested in what happens when we take the Hamiltonian vector field of f, and what direction does that point at xc. So I have to take the function f of xk, evaluate it at xc, and put it into this formula. So, well, that's the same, evaluating the function f of xk at xc, that's the pairing between xk and xc. I'm taking the Hamiltonian vector field of f, so I'm putting in f into the second slot. I think this is right. This is one of these, like, you have to make some choice and there will be a sign that changes if you make a different choice, but it doesn't matter very much. I think I want to take df dxj, and then that's multiplied by the vector field ddxi, which remains there as my kind of loose vector field. So where xc comes in is I evaluate the functions there, and where f comes in is I evaluate half of, one slot of the bivector against df, and then leave the other one there to give me a vector field. All right. Yeah, maybe that would have been another good answer to what xf is when you asked, oops. xf is pi of blank wedge f, which gives me a vector field, since I've contracted away one of the vector field slots and left the other one in place. All right, cool. So we manipulate this formula a little bit, and in particular, we look at this appearance of the structure coefficients. So what we're getting here is, if we think of df evaluated at c, so that's an element of the cotangent space to G star, so it's an element of the Lie algebra, and we call that y. So oops, here, by definition, y is equal to the sum df dxj times xj. And this df dxj, that's evaluated at xc, and similarly here, that's evaluated at xc. So when I look at this part of the formula, I'm actually just getting the formula for the evaluation of xc at xi wedge y. All right, and that's just thinking through what the structure coefficients are, right? If I hadn't paired with xc, this would be a formula for the bracket of xi and y. And then I'm just pairing with xc, and so I'm getting xc evaluated against that guy. times ddxi. So thinking of my vector at that point as an element of G star, it's X maps to C applied to X bracket Y. Right, this formula here is telling me I choose some basis and I get the dual basis ddxi times the evaluation of this on the different guys in my basis. So that's just the same as saying it's the linear map that sends X to C of the Lie bracket of X and Y. And you stare at that formula for a little bit and you say, oh, that's actually the derivative of the co-adjoint action with respect to Y. So we haven't talked in detail about how representations of Lie groups and Lie algebras are related. So I'm just writing out the formula here, right? This guy on the left-hand side, that's actually the same as looking at the co-adjoint action of e t to the y, and taking the derivative of that at t equals 0. I just kind of wrote out the formulas for how this goes, right? By definition, the co-adjoint action on Xi paired with X is the same as Xi paired with the adjoint action on X of the inverse, so e to the minus ty. And then the right-hand side, I can use the fact that this derivative, so the derivative on the right-hand side, that's one of the definitions of Lie bracket, and it's xy because that's minus y. So I'm absorbing the minus sign and swapping the order of x and y. And so I get exactly that. The derivative of Xi under the adjoint action with respect to e to the ty is exactly this map. X goes to Xi of x bracket y. All right, and you can think of this as a representation of the Lie algebra, G on the space G star, which is also called the coadjoint action. So just saying, this is the coadjoint action of G, the Lie algebra on G star. And if you have studied the representation theory of Lie algebras a little bit, you'll recognize this formula. Xi maps to Xi, and now I'll write them in the right order. Minus y. X is the definition of the dual of the adjoint action. Right, so this minus sign is a standard thing that always comes up when you take the dual of a Lie algebra action because of the stuff about pre and post composing. It's the same reason you take the inverse when you're defining the coadjoint action of the group. All right, so what does this calculation tell us? What this calculation tells us is that when I put in a linear function, which I can think of as an element of the Lie algebra, and I take its Hamiltonian vector field, that's the vector field associated to y under the coadjoint G action, right? I'm getting exactly, I let the group G act by the coadjoint action of the group, and then I differentiate that and take the corresponding vector field. So if I take a linear function, I take its Hamiltonian vector field, and I take its flow, then what I get is exactly the coadjoint action of e to the ty. That's what this calculation has shown me. So I can, in purely Poisson terms, write the action of the element of the Lie group, e to the ty. Now, not every element of the group can be written as e to the ty. The most important obstruction is, of course, e to the ty for any y and any t is in the connected component of the identity. So this can never find out anything about stuff that's happening outside the component of the identity in the group. Every element of the connected component of the identity can be written as a product of elements of the form e to the ty. Maybe not directly of that form, but as a product of finitely many of those. All right. So what this is showing is that this connected component of the identity G0, this is connected component of the identity, has to preserve symplectic leaves, right? If I act on any element of G star by something in the component of the identity, I might as well just assume my group is connected and spare myself saying that. Then I stay inside the same symplectic leaf because I'm getting something equivalent under this equivalence relation of flow with a Hamiltonian vector field. All right, on the other hand, the orbits of the connected component of the identity are themselves Poisson submanifolds, right? We've already calculated that the Hamiltonian vector fields are always tangent to these orbits. So I must have already found the symplectic leaves. Right? So each symplectic leaf must be a union of these orbits, but since the orbits are already Poisson, they have to themselves be symplectic leaves. All right, and basically the way you should apply this theorem is you should just assume that the group G is connected at the start, and you won't have to say all this stuff about the connected components. Anyway, so for any Lie algebra G, the coadjoint orbits, well, those are Poisson submanifolds, and the Poisson structure on them is symplectic. So my definition of the symplectic structure on a coadjoint orbit is I look at the induced Poisson structure by KKS, and then I say, that's non-degenerate. Great. So take whatever the resulting symplectic structure is. And the important property that this symplectic structure has is that when I just include the coadjoint orbit into G star in the obvious way, well, think about the calculation I did before, right? I can get the vector field that corresponds to the flow of every element of the Lie algebra by just taking the linear function on G star itself and restricting it to the coadjoint orbit. So that's actually telling me that the naive inclusion of the coadjoint orbit into G star is a moment map for the coadjoint G action. This is kind of it's a cool theorem, right? Like, let's just think about this. What I found, so Canis de Silva, oops. So for all X in this Lie algebra, or I should use Y because X is a Hamiltonian vector field, I found that Y sub O, so this is the vector field induced by the coadjoint action. is equal to the Hamiltonian vector field of f sub y. So Hamiltonian vector field of f sub y for the KKS Poisson structure. So I found a consistent way of picking a Hamiltonian function for each element of the Lie algebra that gives me back the vector field corresponding to its action. And that's the definition of a moment map. This map is obviously equivariant, so the only thing I need to check is that it's giving me Hamiltonian functions for the action of every element of the Lie algebra. And indeed it does. Questions? Yeah, and this is one of these theorems that's like kind of miraculous. And then you just get used to it. It becomes part of the furniture of your life. So a worthwhile example to think about is when G is abelian. So when G is abelian, the Lie bracket on the Lie algebra is trivial. So the corresponding KKS Poisson structure is trivial. And so each point is its own symplectic leaf. And indeed, the coadjoint action is trivial as well. So every point is its own coadjoint orbit as well. So it all works out. That's great. For SO3, so we've already done a bunch of calculations for SO3. So I haven't, maybe haven't written this out extremely carefully, but it should be plausible that I can identify, or I should have said the dual of the Lie algebra, with R3 with the usual rotation action. I mean, the Lie algebra is three-dimensional, so is its dual. Well, what other three-dimensional representation of SO3 could it be? Now you can also sort of actually directly calculate this from the calculations we did before with anti-symmetric 3x3 matrices. So like, not expecting you to just completely take this on faith, but it's should be pretty plausible. I mean, the point here is that, what truly the definition of the adjoint action on SO3 is the action of SO3 by conjugation. And so you need to calculate that that's the same as the usual action on R3 by multiplication, which takes some amount of work, but it's just writing out a matrix calculation. And the representation of R3, of SO3 on R3 by rotation is self-dual, right? When you take the dual representation, you take inverse transpose of the matrices. By definition, that's giving you the original matrix back. So it doesn't change when you take the dual. All right. So in this case, I have one lone point given by the origin, and then everything else is giving me a sphere. There's actually some slightly complicated calculation you have to do to check what the volumes of those different spheres with respect to the symplectic form is. I didn't quite feel up to writing all of that out, but you can do it. But of course, it's going to be a multiple of the usual round volume form on the sphere. So since we've talked about it quite a bit, I wanted to do another interesting example, which is the Heisenberg. I think the last time I had actually lied about what the Heisenberg Lie algebra is, and told you about the solve. Well, yeah, I don't know. I guess it probably depends who you talk to. I at least lied to you about what the right definition of the Heisenberg group is, which is that you have strictly upper triangular 3x3 matrices. So as discussed before, if I were going to take the adjoint action, I would look at just conjugation of strictly upper triangular 3x3 matrices. So to get the co-adjoint action, I need to take the dual thing. I need to take all matrices modulo the subspace of upper triangular ones. So this is sort of, in this case, what's different between the usual guy and the dual, the adjoint and the co-adjoint. And this again has to do with this, like when you take dual representation, you take inverse transpose of your matrices. And if you are doing conjugation and you take inverse transpose of that, you'll see what you have to do is conjugate the guy in the middle. Okay. So I have to look at these strictly lower triangular guys and just throw out anything that happens on the diagonal or above. I'm modding out by that space, and I have to look at the action on these guys. And what do I find? Well, I find that when I act, I leave Z fixed, that's unchanged by the co-adjoint action. And I do this funny translation on X and Y, which depends on which guy I acted by, on the off, just off diagonal entries here, and on the value of Z. So this preserves level sets of Z. And if Z is not 0, then my Heisenberg acts transitively, right? I can arrange for BZ minus AZ to be any value I want, as long as Z is not 0. And so I can act transitively on the whole thing. It's basically a scaled version of the translation action of R2, but with a rotation. And you'll note here, this co-adjoint orbit of the Heisenberg is exactly the action on R2 we had before that didn't have a moment. Right, so we had talked before about how if you have, oops, R2, that acts on itself by left translation, that's a symplectic action, but it has no moment map. And one of the ways to fix that is to think of R2 as a quotient of the Heisenberg group, as I defined it there. I get an induced action of the Heisenberg here, and that has a moment map. Precisely because of this calculation we did, that the Lie algebra of the Heisenberg is isomorphic to the span of X, Y, and 1 under a Poisson bracket. And what we then found was that we had a moment map into the dual Lie algebra of the Heisenberg. And this is actually an isomorphism onto one of these levels. I mean, all of them are isomorphic to each other by scalar multiplication. So I'm getting one of the sort of non-trivial symplectic leaves in the dual of the Heisenberg Lie algebra. On the other hand, if Z equals 0, then the action is trivial and the co-adjoint orbits on the level Z equals 0 are just individual points. So sort of the picture here is my levels where z is not 0 are just planes. And then there's one plane in the middle where I'm just getting each individual point as its own symplectic leaf. So this is kind of useful for thinking about how sort of the structure of these Poisson structures that are neither symplectic nor 0 go, that you can have this like sudden drop in the dimension of the symplectic leaves because the Poisson bivector suddenly becomes more degenerate, and wham, your symplectic leaves shrink down, and so you have many more of them. And there are lots of other examples like this. This is a really typical kind of behavior. And if you write out what the Poisson bivector is, like, right, what's happening here is these guys at z equals 0, those are fixed under the coadjoint action. Whereas if you move away, the coadjoint action starts translating you around this plane. And maybe I'll just note, if you look at the adjoint action instead, so this is the coadjoint action. And this Heisenberg is a great example of how you can have different adjoint and coadjoint actions. In the adjoint action, you have a map to R2, which is equivariant. And so the orbits of the adjoint action look like there are a bunch of lines, one for each non-zero element of R2. So each one of these sits over some xy, and then over 0, 0, the adjoint action is trivial. And you just get a bunch of disconnected points. And you'll note here, right, this couldn't be symplectic. They're a bunch of one-dimensional things. But somehow magically it works out that in the coadjoint orbit action, the orbits are always even dimensional. This is a not at all obvious fact if you are not thinking about the symplectic structure. It's kind of surprising, but it magically works out. And I'll just note here, right, like what's happening here is each one of these orbits, these are the matrices of the form 0, 0, x, y, star. And the Heisenberg acts transitively on matrices like that as long as x and y are not 0, and acts trivially on them if x and y are 0. All right, are there any questions? Since I have a couple minutes left, let me say one more thing. Like what's so interesting about Poisson structures? Well, actually, this Kosten-Kirillov-Suryow structure is a special case of an even richer and more interesting class of Poisson manifolds, which are what are called Poisson-Lie groups. Somehow for me, these are like the source of interesting Poisson manifolds. I'm sure if you talk to somebody else, they would tell you some completely different kind of perspective that Poisson manifolds show up from. So what are Poisson-Lie groups? These are Lie groups, G with a Poisson bivector pi such that the multiplication map is a Poisson map. So I should say here what a Poisson map is, right? So I have this map M. What I mean is if I have two functions f and g, I can take their Poisson bracket and pull that back by the map f. So here f and g are smooth functions from G to R, or I can pull each one back separately and take their Poisson bracket upstairs. So this is a generalization of a Poisson submanifold. Poisson submanifold is an inclusion of a submanifold with a Poisson structure, which is a Poisson map. All right. And G star is actually an example. Where the underlying Lie group structure is just boring old addition. Plus and the KKS structure. But there are other examples which are sort of interesting Lie groups and interesting Poisson structures. For example, any semi-simple Lie group has what's called a standard Poisson Lie structure. And given that I'm supposed to be wrapping up in 3 minutes, I won't try to explain what this is. I'll just say it's non-trivial and interesting. And where it comes from is actually sort of a classical limit, or I should say semi-classical limit. Of what's called a quantum group. So one version of a quantum group is taking the functions on this group and deforming them to non-commutative algebra. And actually this standard Poisson Lie structure comes from kind of the most famous way of doing this, and then looking at what is the leading order bit of taking commutator of two functions after I do this deformation to a non-commutative algebra. So these Poisson Lie structures, they're very important if you want to understand things about quantum groups, where sort of somehow this KKS comes from like kind of something which kind of isn't deformed at all in the quantum group direction. So somehow like KKS, this is something about like precisely because the addition on it is just kind of boring. It belongs in kind of the usual Lie group world. It's when you have sort of an interesting Lie group and an interesting Poisson structure that this is telling you something about quantum group land. Yeah, maybe that's all I'll say for the moment. Are there any questions? Yeah, maybe I'll say one thing about this, since maybe this is something I should put as like a possible final project topic or something. These structures of Poisson Lie groups actually come from what are called Lie bialgebra structures. Oops. Which is when you have, well, a usual Lie group structure from the second wedge power of G to G, a Lie bracket, and then a Lie co-bracket, which you can write in a couple of different ways, either as a map from G to second wedge power, or to as a Lie bracket on the dual space. And so a usual Lie group with the zero Poisson structure corresponds to a usual Lie algebra plus the trivial co-bracket. And on the other hand, G star with KKS corresponds to the trivial bracket on G dual, and the co-bracket being the Lie algebra structure on G. So this sort of standard Poisson Lie structure comes from some interesting co-bracket on semi-simple Lie algebras, which I could explain, but it would take a little while. Josh.
Yeah, I do have kind of sort of what you'd say, kind of a vague question about co-algebras, which is that I've always found them to be kind of confusing in the sense that I'm never quite sure what this map into the tensor product or the exterior product is supposed to be doing. Like, what does it tell us?
Well, so one thing it tells us is this Poisson Lie structure. Right. I mean, yeah, that's a fair question. So, I mean, in this context, indeed, what you could be thinking of it as doing is giving you this Poisson Lie structure. Sorry, I didn't think I would have time to talk about this, so I didn't prep it carefully. I mean, one way that, yeah, maybe that's sort of all I'll say, that it, like, right, if you think that Poisson Lie groups are kind of a natural thing, you'll actually be like led very directly to this notion of a co-bracket. It's like exactly what you need to get a Poisson Lie structure. And just, like, it's been a while since I've looked at the formula, so it has to do with like, you take this co-bracket thought of as a tensor and you take the difference of pushing it forward by left and right translation. It's just one of those like, oh, I didn't carefully check what the formulas were before this. And that's probably the best answer I have. That, like, this Poisson Lie thing is very natural. It comes out of this quantum group world. And so I guess the sort of other thing you could say is, right, there's this notion of kind of duality, that you can take the dual space and swap the roles of the bracket and the co-bracket. And this corresponds to taking dual of Hopf algebras. So sort of the famous example of this is if you want to think about these as Hopf algebras, right?
So
this turns into functions on G. This turns into the universal enveloping algebra. And there's a natural pairing between these. You can think of the universal enveloping algebra as differential operators, and you're differentiating the function and evaluating it at 0.
okay, so there's a relation between the Lie bialgebra you were talking about and Hopf algebras.
Yes.
Okay, is it a Hopf algebra?
No, it's the, yeah, what's the very way to say this? That, so the co-bracket, so just as the Poisson bracket is what happens when you take the multiplication in a deformed algebra and look at the first order part of bracket as you send your deformation parameter to 0, the co-bracket is what happens when you look at the co-multiplication in a deformed algebra and look at the limit as your the parameter of your co-multiplication goes to 0.
Question about that. When you deform an algebra, I mean, there's lots of different ways of deforming it, right? Are you saying this falls out no matter how you deform?
No, I'm saying you have to be careful. Like,
Is there a special
but
thing?
I'm not going into details here about exactly how this comes out, and I don't want to.
Fair enough.
I want to be careful that I would need to prepare to
Okay.
say all the details, right?
But earlier, when you talked about the Poisson bracket as being like the first order term in this deformation of the functions, you were referring to a specific deformation, right? That you didn't tell us what it was. Or,
and again, like so there's this slogan people say, which is quantization is an art, not a functor.
okay.
Right? So if you have a quantization, then a star product, then there's a corresponding Poisson structure that comes from looking at the first order of commutator as you go down to 0, as you send your deformation parameter to 0. But it's a very hard question given a Poisson structure. Like, how do you construct a non-commutative algebra from it? So there's at least a version of that question where the answer is yes, but Kontsevich got a Fields Medal for proving it.
Okay. Okay, thanks.
Sorry, was that?
I was saying, I'm sorry, who got a Fields Medal?
Kontsevich.
Kontsevich, okay.
Yes.
Oh, by the way, just a practical question.
What?
Would it be possible to get today's lecture notes, like the board, in any form? Is that already?
Oh, yeah, sorry, I've been a little lazy about putting those up, but yes.
Okay, great, thanks.
Yeah, sorry, I will catch up on posting lecture notes. All right. I'll stop the recording.